Let's take a look at some additional exponential models, and we're going to start with some quantities that involve continuous growth or decay. And if we take a look at just some function values, so suppose we had an account of $100 with 5% interest compounded annually versus $100 with 5% annual interest compounded continuously. And so it's hard to imagine, but let's just take a look at what happens to the balance over time. Okay, and we can see how initially the deposit was the same, but even after 1 year, the balance in the second account is a little bit more. And you see as the years progress, the difference between their balances becomes even greater. Okay, and so that's what's going to happen when you have an exponential function that has a continuous growth rate. Okay, so typically these functions are of the form y equals a naught times e to the kt, where a naught is the initial quantity, which also corresponds to the y-intercept. K is the growth or decay rate. And so in this graph that is given, this is the function f of x equals e to the 0.5x. Okay, so we see some clear things from the graph and from the equation. First, the y-intercept is 1, right? It's just the coefficient of this power. And I see from the graph that this is true. Okay, next, we can tell something from k, which is a positive value, and we see how the graph of this function is increasing. If, on the other hand, we had another function, which was e to the negative 0.5x, okay, this one, we can tell just graphically what's going to happen using transformations because of that negative, that there's going to be a reflection of the graph across the y-axis. Okay, so well, what happens then, we see that the function is decreasing, but it still has a y-intercept of 1, but would look something like this instead. So altogether, we can say that if k is greater than 0, the function will be growing, but if k is less than 0, then the function will be decaying. And we also have some helpful formulas to convert between k and t. And we'll try to derive this formula. So imagine that we take an initial quantity and we double it. It really doesn't matter what the initial quantity is, that the relationship between the two is this factor of 2. So we have a naught is the initial amount, and 2 times a naught is the later amount, and then e to the k times t. Okay, we can cancel out a naught on each side, and then we get 2 is equal to e to the kt. And at this point, we're going to rewrite using a logarithm. And so we can transform it to logarithmic form, or just take natural log of each side, whichever option you would like to take. So I recognize that the base of this power is e, so I'll use natural log of 2 is equal to the exponent kt. And now we solve for k or t, doesn't matter. If we solve for k, we get natural log of 2 over t. If we solved for t, we'd get natural log of 2 over k. You can do a similar thing with half-life, and so half-life you would place a half on the left instead of a 2, and then solve. Notice which sign to use in the formula depending if you are doubling or halving. And so doubling, we have a positive fraction. Halving will have a negative result. Let's take a look at some examples. So suppose a colony of E. coli bacteria doubles every 4 days. We want to determine a formula modeling the number of bacteria present after t days. Okay, so we are going to assume continuous growth and write our formula in the form A of t is equal to A naught e to the kt. Well, we do have the doubling time. Okay, that is given. And we also know the initial population. So we'll substitute 50,000 for A naught. And E, we do need to know what K is, so we'll do a little bit of scratch work. Because we've already done the hard work, there is this conversion to go back and forth between K, which is the growth rate, and T, which is the doubling time. And that is that K is equal to natural log of 2 divided by T. Okay, in this case, we're given that T, the doubling time, is 4 days. So natural log of 2 over 4, and we get about 0.17329. Round out kind of far for these decimals, unless told otherwise. So altogether, our formula is A of t is equal to 50,000 e to the 0.17329 t. And in part B, we're asked to find when the colony will reach 300,000. Okay, so that's an A value. And so we have 300,000 is equal to 50,000 e to the 0.17329 t. And we will solve this equation for t. So the first thing is to isolate the power. We'll divide each side by 50,000. And we find that 6 is equal to e to the 0.17329 t. Rewrite in logarithmic form. So we have natural log with base e. So natural log of 6 is equal to the exponent 0.17329t, and then divide both sides by that decimal. And evaluate on your calculator. And that gives us about 10.3, which is 10.3 days.